We now turn our attention to trying to find new rings given the rings we've already had. And that is maybe that inside of our rings, there are subsets that are actually rings in their own right. And you've seen some examples of this. There's sort of this chain of inclusions. Of course, none of these are equal, so I can get rid of the or equal to part. And so a lot of the number systems you encounter when you're an undergraduate fall into one of these four categories. And, they're certainly contained in each other. And what this is saying is sort of inside of Q, there is a ring, which we refer to as Z. In fact, there might be more than just Z, but there's definitely at least Z. Similarly, inside of R, we have Q and Z. So R has at least two rings inside of it. In fact, it has a lot more than just two, but it has at least two in this chain of inclusions. And then C has all of the complex numbers, has all of these three. And in fact, C has quite a lot of different subrings of it. So different subsets that happen to be rings. So let's define the term, and let's do some silly examples, and then we're going to try to deduce a test for whether or not a subset is a ring. And so let's do exactly that. So definition, suppose we have a ring R and we have a subset S of R. Great. If S is itself a ring under plus and multiplication, plus and dot, whatever the plus and dot is for R, then we say that S is a subring of R. Great. So it's a subset which happens to be a ring with the same plus and dot as in R. So it's gifted the addition and multiplication from R. So let's look at some examples of subrings. Let's do a silly example first. Well, Z is contained in Q, and Z is a ring under the usual addition in Q. So it's a subring. Subset, which is also a ring with the same operations. All right, let's do a slightly less trivial example. Z is contained in Z adjoin X as the constant polynomials. The polynomials that are output a constant. Addition of constant polynomials and multiplication of constant polynomials is the same as addition and multiplication of integers. For some meaning of the word the same. It's effectively the same as plus dot in Z. Thus, Z is a subring of Z adjoin X. Fantastic. Let's do another slightly more involved example. We saw that 2 by 2 matrices over R is a ring, and we can view the real numbers as a subset via any real number is viewed as lambda times the 2 by 2 identity, where I2 is the 2 by 2 identity. Great. And so, with matrix addition and multiplication, lambda I2 plus mu2 is factor out the identity, and lambda I2 times mu I2 is, well, the identity times anything is itself. So if we multiply the identity, we associate cleverly, we multiply the identity with anything, we get that back. So what I'm getting at here is the addition and multiplication when viewing R as a subset of M2R 2 by 2 matrices over R, the addition and multiplication are the same as they are in R. Now technically, if you've seen homomorphisms before, technically there's a homomorphism in the background, but we're just going to think about the copy of R inside of M2R as what are called diagonal matrices, as the same as R. We'll worry about what the same as later on in this class. Okay, so the addition and multiplication are the same rules as they are in R, so R is a subring of M2R. More generally, if R is any ring, then 2 by 2 matrices over that ring R has R as a subring. Via scalar matrices, as above. Okay, so these are all great examples of subrings, in addition to the chain of inclusions we had at the beginning. In the next video, we're going to develop a test to determine if what we have is indeed a subring.